So here we are at video 3. This is going to take an overview of LIN Bus. So we'll look at LIN Bus. Here I'll start with slide 1, a maximum speed of 20 kilobit per second. And that's what it looks like. There's our waveform. But we'll take a step-by-step guide, breaking it right the way down, starting with what is LIN Bus. So it's a single wire bus with voltage driven from 0 volts, to 0 volts. It's pulled down from a recessive 12 volts. So it's always at 12 volt. When you hear that term recessive, it's where does the bus rest? For binary signaling and communication. A single wire bus connects to a commander ECU and all responder ECUs. So that single wire, if you look at the diagram on the right hand side, you see that single wire just passes across from the commander to the responders. Traditionally known as master-slave. That is how it's written in the specification. Obviously we use these terms now. LIN communication is bidirectional, deterministic and controlled solely by the commander. So basically nobody speaks without a request from the commander ECU. And typical LIN bus baud rates, there's that term, baud rate, utilised for transmission includes 9.6 and 19.2 kilobit per second. You'll see when you use the decoder feature of PicoScope how these can automatically be selected. You see there, I've just put a little diagram that shows us the voltages and how it relates to bits and bytes. As the voltage goes up, that denotes a 1, and as it drops down to a certain level, denotes a 0. So why do we have LIN Bus? Low cost protocol using standardized components. Allows vehicle manufacturers the flexibility to customize the data exchange. So this is something that's quite important to VMs. They can almost make these standardized protocols their own and include quite often sometimes that what I've discovered deviate from spec.
Yeah, very much so.
The real world, yeah. LIN incorporates diagnostic support so we can communicate with these ECUs. And it's been adopted by the majority of vehicle manufacturers, so maintaining low cost. So there's a cost issue again. The fact that it's one standardized and it's used by everybody means it keeps the cost down. ISO approved and documentation under ISO 17897, and whilst these papers are expensive, you can purchase them. Sometimes they're out there if you're lucky enough and you search long enough, but they carry all the, how would you describe it, Andy, an ISO paper, the nooks and crannies of a network?
Well, it's the standard.
The standard, yeah.
And it defines it down to almost the creating of the LIN protocol right down to that level. So quite often if you do go down a rabbit hole and find the standard, some of the stuff that you'll be reading won't be applicable to the test and measurement side of stuff. But understanding the network and how it's put together can be beneficial, and that's why we're doing this overview video. We're going to give you enough information in this short little video so that you understand LIN, and then you can apply what you've learned about LIN to other single wire networks, because there are other ones. We're just looking at LIN today.
So that you mentioned on that as an overview, great. Hopefully it enthuses you to dig deeper, because there's so much to be revealed when you start moving and digging down into these networks. So where do we find LIN Bus? Well, it's perfectly suited to low priority, low speed, convenience features. I find it amazing we're calling 20 kilobits per second low speed.
Yeah.
There we are.
I think it's important to say, where you say where we find them, there are things that normally have a manual override. That's I think that's a key thing, because it's not as fault tolerant.
Yes.
You often find LIN where you can have a manual override.
Yes.
So where you've got examples you've used there, climate control, door locks, and windows and seats, you can still operate them manually.
Yes, yeah. Yeah, typically LIN applications include climate control, etc. Yeah, LIN can be found in vehicles from 1999 in version 1.0 to the present day, where we're on 2.2a. Now, if you start looking into the protocol, and I've covered some of this in some of the forum posts that I will put up out there digging a little bit deeper, that there is often compatibility, backward compatibility between these components, but it's not as seamless as you may think. Often a commander ECU will work with older responder ECUs, but not the other way round. And where I've seen this in the real world is with alternators. Yeah, pattern parts, these kind of things, and then you still end up with communication errors simply because the device has LIN on board, but it is a different version. So how does LIN Bus communicate? Here is the transceiver that's inside a LIN ECU. Only the commander ECU allocates the messages on the bus, so certainly initiates the thing. So every packet that we'll see on the bus will contain information from the commander. The LIN Bus is biased to battery voltage via a diode and a 1 kilo ohm pull-up resistor at the commander ECU. So this is the transceiver for the commander. So we'll see there that we have our plus voltage, which is 12 volts, through the pull-up resistor, through the diode, onto the bus. And then of course when the transistor switches and pulls that down to ground, we'll change the voltage from a recessive level at 12 volts down to 0 volts. Each responder ECU on a LIN Bus is biased to battery voltage via a diode and a 30 kilo ohm pull-up resistor. So there's a little element of diagnostics here in that if we measure the value of the pull-up resistor inside the ECU that we're working with, we might have an indication, I say might, it could have a fault, of what ECU we are connected to. Is it a responder or is it the commander? As you'll see when we carry out this test, the spec is not always in real world. Please don't think that 30 kilo ohms is what every ECU will be, every responder, not the case. LIN Bus communication is via two states, 0 volts and 12 volts.
I think it's important, though we've said 0 volts and 12 volts there.
Yeah.
They're reference to 0 and reference to battery voltage.
Yes. Good point, because that in real world we'll see something a little different. The transceivers within the ECUs pull the LIN Bus voltage down from the biased 12 volts to near 0 volts during signalling, i.e. communication. And whilst there are several LIN buses on a vehicle, each LIN Bus has only one commander ECU. So you might have groups of LIN buses, but each one will have a commander. The LIN Bus has only two states. Well, we mentioned it has 0 and 12, and that's two states to denote a logic 1 and a 0. Recessive, the high state LIN Bus at 12 volt denotes logic 1. Dominant, the low state LIN Bus close to 0 volts denotes logic 0. It's worth noting that because you'll see that in the decoder, the PicoScope decoder, when we decode, certainly in binary, just see the ones and zeros and how they align with the pulses in the pulse train. So what are the characteristic features of LIN? Let's go through. No communication on the LIN Bus without permission from the commander. So the commander drives everything. The commander ECU may also contain a responder, so the commander may ask for a response from itself, and there is a way to reveal that when you actually look at the LIN Bus voltage levels. Each LIN network commander ECU can be connected to a maximum number of 15 responder ECUs. So it seems a lot, doesn't it? 15 on a LIN Bus.
Don't think I've ever seen that many.
No. I was thinking maybe climate, perhaps with the various motors if they're all intelligent, but it seems a lot to me. A LIN Bus network length is no greater than 40 meters. The LIN Bus received voltages will differ from battery voltage due to impedance characteristics, which in turn serves as a means to diagnose a short to battery positive. So we've talked about there about recessive voltage being battery voltage. Here's one of those scenarios where not quite when you actually measure in the real world, there's a reason for that. We want to be able to diagnose a short to battery positive, so how do we do that? Well, we'll see when we measure for real. And a Commander ECU can act as a gateway for relaying, translating, converting LIN messages to other networks such as C.A.N. So in the diagram here we see we've got the LIN Commander, which also doubles up as a C.A.N device with built-in gateway. That could actually be instrumentation, couldn't it? Typical or standalone gateway even. All right, so what does LIN look like? So here is a single LIN message known as a packet. When you look in the PicoScope decoder, you'll see this word packet. Every packet has a message, a complete formation that has all the information transmitted in one packet. And here it's captured and decoded with PicoScope. The header consists of a break. So that's the Commander ECU indicates start of message. We have synchronization that sends a hex OX55 sync to allow the responders time to synchronize. Point 3 here is the protected identifier, including the frame ID. The Commander sends both the protected identifier and the frame ID to instruct the relevant responders to respond, listen or ignore the request. Now there is a lot of diagnostic information in the frame ID. That will give us a clue as to what ID is assigned to the computer that you're working with. Let's say you've lost communication with air conditioning pressure switch, for example. If we knew the ID of that switch, then we might be able to prove whether or not that device, that smart sensor, smart switch, is transmitting or not. Then within the same packet, and this is what's unique to LIN, within one packet you have information in the header sent from the Commander and a response from the responder. So the packet, if you like, we split that in two. The header has all the information from the Commander, and the tail, if you like, has the data from the responder and also a checksum as well. So think of that packet being split in two, with the header section having the request from the Commander and then the response from the responder in the later section. And finally there, point A above in our example reveals the baud rate. Remember we talked about measuring the smallest bit? Well, here we have a single bit time of 52.09 microseconds, which gives us 19.2 kilohertz, a baud rate of 19.2 kilobit per second.
So that effectively broken down into language someone may understand. Means basically that the Commander initiates communication, and the Commander initiates communication with a specific node, and only that node can respond to the Commander at that time. So unlike other networks that can talk whenever they want, on a LIN network you can only speak when you're spoken to. So very polite.
Yeah, a good analogy actually, and it's interesting to see just purely from the voltages how we can tell.
And yeah, that's diagnostic gold then.
Yeah.
Once you know that fact about LIN, you can then use that information, that knowledge, that you can look at the Commander and then the responses, and then you can see whether or not you're getting a response at certain times. So knowing this stuff at a sort of deeper level, although it seems unnecessary at first, diagnostically this is great information, knowing that the Commander requests a response and it should get that response. You'll also see if things are not fitted on the network but could be, you'll see a Commander request and no response. That's totally intentional. You've got to be aware of that. That wouldn't be a fault. And knowing this stuff at this level provides you with that. Just that enough information to provide you with some great diagnostic gold.
Yeah, I'm glad you said that, because here, if you look in the decode table, you'll see a red line there which is flagging an error. That may well be that exact Commander requesting a response, but there is no response because that device is simply not part of the network. That's tolerated. That doesn't introduce a fault code. That is part of how that system works. So really in this packet, two golden pieces of information. One is the frame ID.
Yep.
and the other is the data field, because the data coming back is from the responder.
Yeah, it's always a response. Call, response, call, response.
Yeah. So we have some tips here about LIN Bus, and hopefully there's some little bits of gold in here. Receiving ECUs will interpret a bus level voltage above 60% of battery voltage as a logic 1. So we've talked about, oh, it must be 0, 12 volts. This is really drilling down to the nooks and crannies of it, that 7.2 volts and above would be considered as a logic 1. So this is giving us room to move a little bit where we may have a resistance in the cable and the voltage has come down. System works as normal.
But it also allows a slightly dodgy battery still to allow communication during cranking.
Yes.
And things like that. So
good point.
These are, if you look at this, 7.2 during cranking is not much headroom there, is there?
No, and quite possible, yeah. So yeah, 7.2, logic 1 as a recessive, and a bus level voltage below 40% of battery voltage as a logic 0. So we've said there that, oh, it pulls down to 0. Well, actually, a receiving ECU that has anything below 4.8 would interpret that as a logic 0.
Yep.
Yeah. Transmitting ECUs will interpret the bus level voltage above 80% of battery voltage as logic 1. So there is a difference between the two. And the level below 20% of battery voltage as logic 0, the dominant. So little bits of information from the specifications that may help. The time span at the smallest bit reveals the baud rate. We have talked about that. The frame ID, this is the little bit of gold, is linked to the responder ECU. So when we're looking for, is our device online, can we identify its frame ID? Any responder ECU can wake the commander from sleep, and so the LIN network. A little bit of gold if you're looking for parasitic drain. We've said here that nobody speaks or spoken to until the commander speaks or requests, but a responder ECU can wake the network. Frame ID values of 0 to 59 decimal, or OX0 to 3B hex, are used for frames carrying data, and we'll prove this. We'll actually see that the component that we're focused on falls directly in those values, both hex and decimal. The commander ECU requests data during a scheduled and allocated packet slot. So you'll see how things are sequential in their request and responses, almost cyclic in fashion.
Often called time-based.
Time-based. Every responder ECU will sleep after 4 seconds of inactivity on the bus. So if you're seeing inactivity on the bus for longer than that time, no command from the commander, yet the bus activity going on, if we can find the ECU responsible for that, it could be that it is a responder that is refuses to go to sleep and tries to wake the network back up. The commander ECU sends the go to sleep request using data, well, 8 bytes there with 0, and all the other bytes are at FF. We've actually seen this on the network. We'll prove this, so we'll wait for the network to go to sleep. We'll use the Pico decoder, zoom in on the last message, and we see there that final request. That's telling every ECU go to sleep. If we see that, then 4 seconds later, we see the network wake back up again without a request from the commander. We're onto something. Voltage deviations in a LIN packet will provide a means to identify responder ECUs. So we'll notice, simply because of the impedance and capacitive characteristics of different components and cables on the network, how each responder ECU has a slightly different level to its pull down voltage. They seem to pull from the same height, but they almost break away at different levels at the bottom towards 0 volts. And we can use that as a little bit of diagnostic gold, and also influence that when we're trying to sort of qualify what we think we've found. So based on that, we'll now move into the workshop and run through a series of practicals that will bring all this theory to life. So thank you for watching. Okay, so here we are with now LIN Bus, looking at a LIN Bus fault, and we're presented with this vehicle with a fault code for communication, and this is with the high pressure air conditioning switch. Well, it's a bit more than a switch, it's a smart switch, it's intelligent, it is LIN Bus. Interesting, Andy, refrigerant pressure 51 bar.
Yeah, it's unlikely to be that in the system. Looks like a default value to me.
Yeah, ambitious. Also accompanying that, high pressure sensor, no signal.
Which is
That's
a communication error.
That's right up our street for this this video series. Yeah, sensor, high pressure sensor, signal improbable. So, as a quick route, if you like, I guess it's that measurement that gives you the best return on your time. We'll go straight in for can messages be sent, because it's dead easy to get to. We've got a breakout lead on the pressure switch here. We just go straight onto the LIN Bus wire, use the guided test, and actually see what's happening at that point. That will prove us very quickly whether we have got some form of communication at least.
Absolutely. The beauty of the C.A.N network testing process is you don't need to do it in order. So we can go can messages be sent, are messages being sent, and node. But in this case, the fault seems to be with the message.
Yeah.
So are they being sent?
It
The
does
sensor is literally right in front of us. It'd be crazy not
to go there
straight there and see if we've got
Yeah.
any LIN activity on this network.
All right, let's run the guided test. So guided tests, communication networks, it's LIN Bus physical layer. When you open the guided test, of course, you've got example connections,
Yeah. The just-in-time learning is fantastic.
example waveforms, yeah, and there's the further guidance, which really breaks down the protocol. We will put more information on the forum, but for what you need to actually take this capture, it's all there in the guided test. Just before we do, to make sure that we are actually on a LIN network and we've not probed a different circuit, a different network, let's take a reference waveform.
So we're just going to have the shadow of a known good LIN waveform in the background.
Yeah, so there it is. We just pull this down here, and then when we run PicoScope,
so we're just connected to the LIN sensor and ground.
all right, and we'll just let that complete the buffer, and we'll zoom into both captures. And it certainly looks like a communication signal to me, that.
So interesting, in the sort of all the literature about LIN Bus, it says it's a 12-0 voltage. Can you just put some cursors on that, Steve?
So let's put this down to 0 volt. And then we'll pull this along to the top there. So we've got 13.58. So yeah, this is actually in ready mode. So DC is active.
Yeah.
So there lies why we don't have 12 volt. The vehicle is charging. Interesting that we don't pull all the way down to 0. There is a threshold. I guess that enables LIN Bus to detect whether there is a short to ground.
It's fault detection.
Yeah.
So we can tell whether there's short to ground. But how do we tell if it's meant to be a 12 volt bus? Why is it at 13.56?
Well, we know that DC is active, so it's charging. Yeah.
Yeah.
But are you referring to how would it know a short to positive?
Well, that's what I'm alluding to. But shouldn't it be 12 volts, Steve? Is that a mistake?
No. In the specs it would say from 12 volts.
That's what I'm getting to.
Oh,
So
okay,
you've got to be very careful.
Yeah.
Because it says 12.0 and we haven't got 12.0. So it's not reference to ground. So is that battery voltage then?
That will not be battery voltage. You've got to have a means to determine whether the LIN Bus
Should we measure that?
Short to positive. Yeah, let's do it. So we should expect to see that be above 13.58. So if we introduce channel B, we put this directly across the battery. Because we've got BNC plus connection, as soon as we connected the test lead to channel B, it recognised the ×1 probe, and we'll remove there we are. Now that is interesting. I just pause that and bring out another ruler. Yeah, well there you are. And let's just zoom in. So in answer to your question then, Andy, how would it know? Clearly.
Yeah, there's a
Yeah.
difference between battery voltage and LIN bus voltage.
Yeah.
So when battery voltage changes then, Steve, would we expect the difference between the LIN pos and the battery pos to remain the same, or is there a difference?
I would expect those to be kept that distance apart.
Is there any way we can prove
And
that?
you're going to ask me if we can improve that goal. Yeah, let's do it. All right. So we'll leave the reference in place.
Can you lock those then, Steve? As a
Yes. So if I lock these rulers here now, oh, actually, because I've used two different rulers, let me bring in, sorry, I've locked. There we go. And they're both on the same range, they're both on the same scale. Lock those in position. So if I turn off ignition,
well,
I
that's
think,
interesting.
is that the proof you were after, Andy?
I mean, visually that looks the same, but if you was to use the lock ruler function,
Yep.
you would be able to hold there, see they're the same all the way through.
Yeah. So that is not coincidence that that's happening. Yeah. So wherever we position those rulers, LIN Bus Plus maintains a certain level below battery plus. So as LIN Bus could always detect a short to positive. Okay, so
that in itself is probably a learning for me today anyway.
before we do any more, save it. We'll put that on the waveform library.
I think that's a great idea, Steve.
So save. We've tested this before, so this was e-golf. This is all populated correctly. We can't put it up to the waveform library yet because we haven't compiled all the channel labels. We know that channel B is battery voltage. We know that, we don't know, we'll say that LIN Bus is unknown because we don't know. We know battery voltage is good. We'll send the current one up to the waveform library, save and upload. Anyway, we digress because
it's all good learning, Steve.
it's all good learning, yeah, but we are looking now for communication. Why do we have a communication error?
So yeah, what we have proved though is the LIN Bus is operational. So if we go back to our C.A.N, R and node, can messages be sent? Well, we don't really need to do much there because messages are being sent.
Yes.
But are messages being sent successfully? That's the next question.
For that then, we would apply a decoder.
Very much so. Or is there anything else we could do first?
Are messages being sent?
Interestingly, we've gone to the regressive state behind it.
Yeah, so LIN Bus is recessive, isn't it? Recessive voltage on LIN Bus is 12 volt.
12 volt.
And it remains so.
And so there's evidence of that, which is quite good. But could we turn the ignition back on, get the LIN Bus back active, pause the scope? Could we then look to see, because isn't it something peculiar about LIN Bus whereby the commander responder, so you've got call response. Can we see if we can see that just by zooming in?
Yep, we can. Okay, so with LIN Bus, we know that in a packet there is two ECUs responsible for forming a complete packet. We have the command and then we have the response. They're coming from different ECUs, so the commander will be powered and ground. We'll certainly have a different ground reference. We assume that everything that is on ground is locked to the same ground. There'll always be what you call electrical signatures. Unique signatures. We would expect to see a difference between the commander pull-down voltage and the responder pull-down voltage. And if we zoom in, we can see that. So let's see if we can find one. In fact, this is probably the best possible example we can see here. Let me just drag this into view. Unlock our signal rulers. Here then we have a command, because we know that will be at the head of the packet. Yeah, and if I just scale up slightly, I think that will help us. I'm just going to remove the reference waveform. And I think now we've discussed the voltage.
Yeah, we can take that off.
We can take that away as well. So what you were referring to, Andy, was this unique signal.
Yeah.
Where we have the header, which pulls down at this stage much lower than the response. Yeah. So we know certainly at this position that the commander sent a request and something responded, but we don't know what. And we are faced with no communication with air conditioning switch or air conditioning pressure switch.
The very packet next to us, which why this was a great place to pause, has a command, no response.
Looks like there is a command, no response. You're absolutely right, yeah.
And then we can identify that because it's at the same.
Yeah. So actually, let's see if we can show that in a better light. If we focus on this area of the waveform here and this area here, we see that they both pull down to the same level. So what you're saying, Andy, is if that is the header, there doesn't appear to be any response thereafter.
No response.
And whereas here there is a command
and no response.
And a response.
And a response.
And a response
but
there,
it's not the response from the same same node. A different node has responded to the command. Which is interesting itself, because we now have on the screen some evidence. We know there's messages being sent.
Yeah.
We know they can be sent because they are, but not all messages are being responded to. Which, in our situation, we know that messages could get there.
Yeah.
But we don't know whether that's our sensor in this right now. But we suspect it could be. So we could go to the next stage, which is node, and check for power and grounds at our switch.
Okay. Before we do that, before node, because it makes sense because we're here. If we put the decoder on there, we would see multiple errors. That would support that we have what we're seeing with the scan tool.
Well, we see an error.
Yeah. I wonder whether we would be, we would know whether or not that would be a header, because within a command, because it will have a specific configuration right at the beginning. We would actually know that that was a command.
Well, let's just bring up the decoder.
Let's do that. Why not?
Before we take another measurement.
Yeah. While we're here.
It's a great idea.
Serial decoding. LIN Bus. Channel A. We'll go for 6 volt. And then the difference between 6 and 12, we'll go for 3 volts. The decoder is selected 19.2 by default. Click next. We'll go with the current buffer and finish. And I think that speaks volumes, doesn't it, there? We see in the decoder table multiple errors. Let's have a zoom in.
Zoom in, let's try and find one of those 2 packets of call and response and call and no response.
I think here we are. I think we could have, there we are. So if I minimize this, if we focus on the waveform on the right, there we have our command. There we have data. Data can only come from the responder. Well, no, the commander could request from itself, nevertheless. In this scenario, though, we have a command, as you said, no response. So this supports what we have found with the scan tool. Based on that, you were right, go to node, power supply to node, see if that brings us back into line, see if we start to get communication.
Yeah, it looks good. Is there anything else we can tell, or anything we can, while we're here, we can glean from the information in front of us? For example, how do we know the baud rate?
Baud rate was chosen, actually, yeah. If we had a baud rate error, that would give us multiple errors in the decoder. So if we measure the smallest bit, if we're quite accurate about this, let's try and go, we'll use the decoder there. 19.6.
Okay, I agree.
Yeah.
Pico got it right.
It did.
But it was worth checking while we were here.
And while we were here, yeah.
Because we've taken the measurement, we might as well get the most out of it. So, in effect, then, Steve, what we've managed to do by taking one measurement is gain quite a bit of information about what's happening on this particular LIN network. Yes, we've got a number of faults, but we kind of guessed that because we got fault codes.
Yes.
We're left now with the next stage, which is checking node for power and ground.
Okay, yeah, so let's go to the chart. When we actually look at what we've got there, the data we've collected, can messages be sent?
Well, yes.
Yeah. Are messages being sent?
They are.
They are.
Are they being...
With errors?
Are they being sent successfully?
No.
And we've got twice the evidence, if you like. We've got the evidence that we could see call, no response.
Yeah.
And now we've got the actual errors on the decoder.
On that, before we actually check node for power and ground, let's send that up to the waveform library.
Great idea.
Save. There we are. So on that, we'll send this up to the waveform library as a bad example. So it's LIN Bus, it's bad, it has a LIN communication error, the current one. Save and upload.
Fantastic.
So anybody who's following along with this can actually pull this waveform down and see the LIN errors. Next then is, as you suggest, power and ground. So let's drag the decoder down. Activate channel B. We're expecting 20 volts, sorry, we're 20 volt range. We're expecting 12 volts at the pressure switch. Leave the decoder. Okay, so we'll measure across. We are referenced to ground.
Ground.
Well, I think that's pretty conclusive. That's no power supply to the node. It is a node, but it's, in this scenario, the node we are referring to as the air conditioning pressure switch. Reference to ground. Blame your measurement before. It doesn't get any better, does it, connection-wise?
No.
There is no power supply to air conditioning pressure switch.
If this was presented in a workshop in this fault state, and we were doing a diagnostic, and we were following the network C.A.N process, we have now got to a crossroads in the job. We suspect we know what's wrong. Mm-hmm. We don't know the cause of what's wrong. And this is the problem when you, it's almost like Eureka now, isn't it? We know what's wrong. But why is there no power there? So we still could have a blown fuse, a broken wire, or something even more sinister. Mm-hmm. So the job's not over.
No.
So now what we need to do, refer to wiring diagrams, find out anything about that circuit, make sure we know the elements within that circuit to test, where to test, what to test before we pick up the meter again or the scope again, because we could save so much time by looking this up first than just blindly prodding around in the fuse box.
Yeah. You mentioned there not following the order there, our message is being sent node. How quick was it to just qualify that sent was present? It was too good an opportunity to miss at that point.
Absolutely. And the fact you've got a signal, implausible signal and a signal error, the temptation would be to test the signal anyway.
Yeah.
If this was a normal sensor and not a LIN, you'd have started there anyway.
Yes.
So it just goes to show that you don't have to modify your procedure too much.
Yeah.
You just have to be aware of what you're measuring and then adapt your procedure accordingly.
Yeah. Wiring diagram wise, the actual item is called G805, and that is pressure sender for refrigerant circuit. And as we follow this through, we see that on the black and blue wire goes through a relay, J32. J32 powers up the pressure switch via power supply, which actually goes to fuse box engine bay, and I think it is fuse 35. So fuse 35 blows, there is nothing here, no power supply. Equally, because it's coming through a relay, it'll be far more than powering just that, which starts to fit with the multiple errors that we've got. So on that note, let's test, let's have a look. So if we have a look at that fuse, we've qualified that fuse is blown. Good question, why is it blown? Yeah. Let's come back out. Let's go back to our waveform. We'll run PicoScope. At the moment, the decoder is showing multiple errors because that is from the previous buffer. I'm hoping now we start to see fewer errors. Already, I think we can see there's a huge change.
Significantly less errors.
Yeah. And let's zoom in on the signals. And we are looking for areas where there is no response. So if we focused on this one here, yeah, we see that there is a request from the commander, but no response. Remember, LIN Bus can have errors. It's not unusual to see repeatable errors. Yeah, in fact, there is exactly what we're looking for in the decoder, is the header, frame ID, but no data in the response.
And that's frame identifier 28. So, although we're fairly certain we've sorted the problem out with our pressure sensor for a refrigeration system, how could we identify a specific node on a LIN network in it sort of maybe a little bit more scientifically by electronic signature, or a little bit more of a quick and dirty method? What can you suggest?
Quick and dirty is always disconnect.
Disconnect. I love a disconnect.
Yeah, disconnect as intrusive as it is, but let's see what effect that would have. So at the moment then, let's run the decoder. Let's remove the zoom. We'll disconnect the power supply. Let's have a look in here. Multiple errors. What was the previous error? Was
28.
28 was there.
And because to be clear, we've only disconnected the power supply to the pressure sensor.
Yes.
So we'd expect only the pressure sensor to join its friend number frame identifier 28.
Yes.
Is that correct?
So, and now we have 24.
24 and 28
yes.
are now not responding.
Yeah.
So could we, with a reasonable degree of certainty, say that 24 is the frame identifier for the refrigerant pressure sensor?
The way to do that is if we run this again, just to play devil's advocate, with half the buffer with it disconnected, half the buffer with it connected, we'll actually see, because we'll know the point, won't we, where we've actually put the power supply on. Let's do that. So let's close the zoom, run PicoScope, connect the power supply. Now I would expect in this buffer to see, well, that's very interesting. If we just focus on the red for a second, just how many errors we have here, and then no errors there. So let's...
Oh, there are some. There's still number 28.
Yeah. But if we do something called decode between rulers, so we move from here. So we're just going to decode data, and we'll look for 24, ID 24, between those 2 points. To decode between the rulers, we need to decode between time rulers. If we look now, we'll see, I think we can safely say the proportion of red here is greater. Yeah. And we'll go to the decoder table, and we want the frame ID contains the value 24. So now we are only searching for 24, and it's at this point here, look, where we go from no data to data.
So can you click that particular decoded frame?
Well, this was the last failed frame.
Okay.
Where frame ID, protected identifier 64, which contains the frame identifier 24. You'll only find 24 in the decoder table. And then we move along to the next packet.
Okay, that's really interesting, because power came on, and because it's time-based, it missed its slot.
Yeah.
So even though power came on, it didn't have chance.
Yes.
But now, after that, it's responding, and there's our good friend 28. Call, no response.
Yeah, and then here we have the first response from the pressure switch.
So what's the electronic signature of the pressure switch?
I think we'll have to change the scaling. Pull this down a little bit. Just to avoid confusion, let's take away channel B.
Yep.
Very slight, isn't it?
It is different.
It is different. So we certainly see here in the header up to protected identifier 64.
Yep.
We have one level, and then the response is at a different level.
Can we measure? It is.
We can measure it, yeah.
It is slight. Only reason I'm going to say is we're going to go to another response, and we're going to measure the difference and see if we can actually see the difference.
In fact, all I've done there is scaled up dramatically. Let's have a look how far we've scaled up. That was done simply by rolling the mouse wheel over the scale. By a factor of 14 now the scale is. Bring down the signal ruler. There's our response. 57 millivolts.
Is the difference between
Yeah.
the commander and the responder.
Yeah.
In this case, our pressure switch.
Command response.
So if we look for a different response, can we see a difference in the electronic signature? Is that another way of identifying a component? We've got the quick and dirty by disconnecting.
Yeah.
We've got frame identifier, and we've got a electronic signature. All different ways of identifying different LIN,
qualifying the LIN.
LIN components.
So that clearly is different there.
Yeah. And that's 290.
Yeah.
So
Yeah.
that the method of electronic signature of identifying components. Obviously, you don't know which one it is, but you can go along and see if there's any differences.
We could prove that further still by adding a resistor. So if we added a resistor into the ground of the pressure sensor,
It would have an impact.
that is going to change. We're going to have a voltage drop
Yeah.
because we've introduced. So let me get something sensible. I think this is about 120 ohm, which is a resistance that sounds familiar. So we're going to need a breakout lead. Okay, so we've added a 120 ohm resistance in the ground for the air conditioning pressure switch. And if we pause there and zoom in, we know exactly where we are. Let's get rid of these rulers for a moment and pull the decoder table down. I think we can safely say there that we have definitely influenced the ground path for our pressure switch, because we've gone from, was it 50 some odd millivolts?
Yeah.
Now to
So
794. So there's the command and there is the response.
So, in theory, we can identify them by placing a resistor,
Yeah.
which will directly call out on the LIN Bus waveform which one it is.
Yeah.
Or we can unplug them. We can look for electronic signatures if we're sure of what it is.
Yeah.
And we can look at frame ID.
Now we know the frame ID, and we've proved that, haven't we, by introducing the fault, introducing the resistance. That qualifies, I think, that we are definitely on the right frame ID. So all in all, no power supply. It sounds easy. Nothing's easy, but no power supply to the pressure switch. Ultimately, that covers other devices on the LIN network. But for now, that's certainly helped us diagnose why we have no communication. If we put the scan tool back on, clear the fault codes, I'm sure we'll have a pressure value. And it would be good to then qualify which bytes are responsible in the pressure switch for reporting pressure, which is something that we can do if we add in a pressure transducer.
Yeah.
LIN Bus faults to discuss. This one is LIN Bus short to positive. We can see at this point here, communication has stopped and our voltage has risen above what would be considered LIN recessive. Remember, there was that separation of about 900 millivolts between physical battery voltage and upper level of LIN Bus. So short to positive, there's an example waveform, of course, of what a good one would look like. Next up then would be this one. This one is the opposite. This is LIN Bus short to ground, and it's a very sporadic one. You can see here there is no LIN Bus messaging ongoing at the moment. This is the recessive state, but we can see during the recessive state, moving the wiring harness, it pulls down. So had there been communication on here, we would have seen that pull down. This is the current flow. So notice that when we do get that short, there is, what's the delta between those two? 13 milliamps of current flow. Now, where is that coming from? Let's have a look here. Let's pull this in. So, for example, let's say the microcontroller is not pulling down to signal. This is a pull-up resistor, and it holds the bus level voltage high. In this scenario here, we see we've got a short to ground. This is just shorting LIN down to ground. So there will be minimal current flow through that pull-up resistor, through the diode, through to ground. And that's what we're seeing there. And here's what we use to our advantage. This is when the responder has a bad earth. So we know that the responder requires a good earth path to pull down to a low voltage. This is the commander making a request. This is the responder responding. In this scenario, it's an aggressive, it's a bad earth. It's 750 ohm. If you remember, let me just bring this image in. If you remember in the video, we actually put 120 ohm resistance in there, and it altered the voltage from the responder, I think from memory about a volt or something like that. But it was clear that there was a difference in the signature between the commander and the responder. Nevertheless, look at the difference there with 750 ohm resistance in the responder. The delta there, 4.8 volts. And we've got a current clamp on here, and it looks like it's got, very little current flow, which there wouldn't be, at that point in time. All right, so 3 faults to contend with, and thank you again for watching.